I think the day after, right?
Day after on Friday? No, I can't. I'll be in Vegas and we'll be.
Oh, that's right.
Yeah, we're gonna be busy.
Take the day before.
The day before.
Or we'll talk about it.
Yeah.
I could have been evil and just said I could give you a 0, but I wasn't. Anything else from homework?
14. How will we know what's going to be on the quiz? Because I noticed in your quizzes, I kind of got thrown off by the questions, and I tried to study it from the book.
Sure.
So
let's talk about this again. How many quizzes of mine have you seen from me?
1.
Okay. What was it about that chapter? Was there very specific? No. Okay.
It was very.
Yes. So it was all about capturing your ideas as to how to solve a problem. I almost cared less about the answer than I did about you showing me what you were trying to do. That was the point of that whole section. So I basically couldn't give you something that I'd already shown you, because then you already know kind of the steps. It was all about, can you come up with the steps? What's the appropriate kind of way to get through the problem? Yes? Number 3? Number
Section 3 points, I'm sorry. Problem section.
3.1b?
No, A.
A, okay. All right, let me see what's going on there. You're going to fall off. All right. So which of the following sets are closed? Ooh, I love this. Okay. You would, John. This one here, right? Before I get all into this, I always get somebody ask me a question like, not that one after I've talked about it for 5 minutes. So, what does closed mean? Why are the whole numbers closed under addition? What does closed mean? The whole numbers are closed under addition. Does anyone remember what that means?
Oh, closed under addition. That means they have to be in the. The same element, like they have to be in the same element, like 1 plus 1 is 2.
Okay, now think about that. So 1 and 1 are both whole numbers, and when I add them, the result is also
in the element.
That's closure. Okay, so what set were we just working with? What set?
Whole numbers.
Whole numbers, good. The entire set of whole numbers. This problem says, all right, what if your set was 1 and 2. Now, really quickly, how can you show that that is not closed? 2 plus 1 is 3. Is the result in this set? No. Do you guys see that? There's a beautiful example, very short, very small. You can actually see everything. That is not closed because 2 elements can be chosen and added together, and the result is not in the set. Maybe? So closed means I contain all the results of every addition of everything in me. That's what it means to be closed. I see people that seem to have a question that they're not asking. Yes?
I first think number. You guys are talking about number 2 or number 3?
3.
Okay, so if it's not closed under addition, I noticed that when you keep adding, like etc., 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 then for A, that would be closed under addition because of how the whole numbers are there. But whole numbers, does that mean whole numbers have to be positive and never a negative?
Exactly. Whole numbers start at what number?
0.
0. And the way to remember that is that's the number that looks like a freaking hole. So that's where they start. And then they go up by 1 forever. So does anyone remember what it's called when I add negative whole numbers in? What that set's called? Starts with an I. Love you guys.
I was thinking
imaginary
numbers.
No. Okay, no. Integers.
Oh, yes.
Yes, okay. All right.
I have a question.
Well, real quick, am I
okay.
all done? Are you okay? Who asked that question? Does that make sense? Okay, I love this question because it's you're working with sets that are a lot smaller. You can see the entire set instead of whole number. You can just see it. Right. Are any of these closed? Can anybody see one of these that's closed?
B and A.
Okay, Emily?
And B.
All right, so
and A,
if you're paying attention, you just got some answers.
and
you got to explain.
And don't forget E.
Yeah, I know about E, but yeah. So explain why. Yeah, I like it. Yes.
Does writing the problem explain why, like showing the work explain why, or do you want us to explain in words?
If you were going to show work here, that would take you the rest of your life because it's dot, dot, dot. Does that make sense? So you have to come up with a way to explain. Now this one you could explain really quick. If the answer is no, that's a quick explanation because you just got to show me it doesn't work. You just got to show me one thing that doesn't work. Counter examples kick ass, right? But it's almost worse if it works because you have to kind of come up with a way to explain to me why it works. For a very small set, I mean, this is really easy, right? This one you can show me everything. What's the only addition problem I can do with this? 0 plus 0. Yeah, I like it.
I have a question.
Yes. Yes.
Number 22 on set B, I have the evidence or like the proof down. I just don't know how to explain why how to convince it to the students that it is always true. I was confused on the reasoning behind it.
All right, let's see. This in here, right?
Yeah.
Oh, yeah. Additive cancellation properties. Oh, okay. I don't want to say too much on this.
I know, because...
Yeah. All right. So additive cancellation. This is what really happened. What would you have done in algebra to go from here to there? What would you have done to both sides?
You would subtract.
Subtracted C, right? So, I mean, this part you should be able to answer, is this property true for all whole numbers? How would you convince your students that it's always true? You could talk about, you don't have to prove it. You just have to show them enough to convince them that it looks like it's true. So can you come up with a couple of examples? Do you see what I'm saying?
Yeah.
Okay.
I mean, I don't know if you just wanted examples.
Yeah, that's
okay.
yeah.
Okay.
Yeah, you don't, in fact, a proof might be too much for the little ones, yeah.
Also, what is I was looking up at 14, and I was just wondering, what is it without comparison? What does that mean?
Oh, again, they just want you to make a word problem that you don't have to use comparison, meaning a word problem using comparison would be, you've got $9, I've got 5. How much more do you have? Do you see how we're comparing each other?
Yeah.
So they mean without comparison, they don't want a problem that involves that kind of situation. So the one about the money falling out of the pocket, that makes sense. You're not comparing two things then. So obviously multiple situations lead to using subtraction, correct? And we're going to see today multiple situations lead to using division. I like it, maybe. Anything else from homework? Okay. So again, next quiz is a week. It is a week from this Thursday, right? My first one, second one there. Bam! You can do it. Yay! All right. So if there's nothing else, oh no. This poor video is playing. Stop it. Okay. Nobody wants to do it. There you go. Okay. So 3.1 was all about addition and subtraction, which sounds very basic. Of course it is. But we have to remember, we're dealing with people that have never done this before. Or maybe they have, maybe they haven't, depending on what their parents have done with them at home. Not surprisingly, we're going to get into multiplication and division. But before I do that, I want to put one thing up here. Okay. So I'm kind of happy I found these same things. This should be a quick question because we just had an example. What could this be? What could I do with this? What kind of situation could I model with what I have up here?
Addition and subtraction.
Yeah. How could I model addition? It would be 5, and then I could just tack that on, and then they can count and get 7, correct? Now, how would I model subtraction using this?
Taking them away.
No. Not with what I have set up. I mean, you could. It's not what I said, but if I just wanted to do it like 5 minus 2, then I could physically take it away.
Why don't you do 7 minus 2 and just take out
So,
the other two?
what I've got set up, what does this seem to be modeling subtraction-wise? All right, I love you guys.
7 minus
So what is 5 minus 2?
3.
Why? Because 2 plus 3 is 5. So what am I modeling? What kind of thing am I modeling? Yeah, what am I missing? What's the missing addend? Right? So I've got 2, and then you can see I'm missing 1, 2, 3. So that's the visual way of thinking about the missing addend, right? Okay. All right, I just was happy I got these. We're going to use these again later for some division problems. Okay. So let's do this. Let's do this. Here. Let's collect some things together, because I think we've got some issues with what happened in section 3.1. Okay. So for addition, I can find my notes on this. We've got the set model, and we have the measurement model. Let me see if I can show you something. Yeah. The measurement one was where we were doing the loops on the number line. Right, so for example, so the set model was where I had like a triangle and a circle plus a square and a diamond and a squiggly. That would equal, I'm not going to draw them all again, that would equal 5. So this would be 2 plus 3 is 5. So that's the set model. Right, that's the set model. Ooh, shit. I love you guys. Don't tell them you can't see it. This looks like biology or something. Two little things coming together. Measurement is when you have a number line. So if I did 2 plus 3, that's 5. Okay, so that's the measurement model. I like it. I like it. Then we had a bunch of properties. We talked about the closure property, commutative property, associative, all those kind of properties. Now for subtraction, we have the takeaway. And of course, that's what you guys were talking about with, if I did 5 minus 2, that's 3, so that's physically taking it away.
Can I see the one on top?
So you get this right.
Can I see the one written on top? Is that the set model?
So this is for addition, set model, and the measurement model. All right. For subtraction, we got the takeaway. They call this an approach. And then we got the missing addend, which is really just making the connection between addition and subtraction. And then they do throw in the comparison on page 95. They talk about the comparison, but that is really just what I said. When you compare two different things, Joe's got 30 of these, Sammy's got 27. How many more does Joe have? Right? That does lead to subtraction. And the weird thing is, we might not see the differences now. If I say that, if I say Joe's got 30, Sam's got 27, how much more does Joe have? Isn't that the same question as I had 30 and I lost 27? How much do I have now? Aren't those kind of the same? They end to the same answer, correct? So we sort of don't see the difference, but students, I mean young people, they will completely think they're completely separate things. That's why it's sort of like you explain the idea in multiple ways, and then you try to show how they're all representing the same idea, right? Okay, so comparison is this little thing they put in on page 95. those like it. Okay, so let's talk about multiplication. What is, all right, let's see what you guys already know. You guys should already know some of this. And I don't mean what's 5 times 3, you know what that is. What's the most basic way to model 5 times 3? What do you guys think? The most basic way to kind of, yeah.
Groups and 3 inside of each.
Okay, I love it. So you can do like a set approach, right?
Yeah.
I love it.
This is 3.2.
Yes, 3.2. Thank you. Oh, this thing is set up to way too bright. Yes. Oh, you're good. So if I had 5 times 3, we could model that as, why did I pick 5 and 3? Oh. We could model that as 5 groups of 3 things. Right, and if I count them all up, I of course get 15. What does that really represent? Yes? Sorry?
5 plus 5 plus 5, or 3 plus 3 plus 3 plus 3.
Yeah, and the funny thing is, now here's what gets people up in arms. And this seems really silly. But we all know that 5 times 3 is the same thing as 3 times 5. Correct? Okay. And let me make sure, I really want to make sure I've got this the right way. Because I normally don't have to worry about that myself. I don't know if I can find it real quick. Officially by Common Core standards, right? Let me see. There we go. The first number indicates how many groups, and the second number indicates how much in each group. Now, do I agree with that completely? No. But it's before they understand commutativity, because that's a whole other thing they have to kind of learn, right? So of course that's what you were just telling me, 5 times 3 is the same thing as 3 times 5. And you could show it, you could start to show it here beautifully. You need to give them, let me see if I can make this make sense, because they don't totally hate the Common Core stuff. You want to give them a framework to live in. So you want to say 5 times 3 means 5 groups of 3 each. So of course, what would 3 times 5 mean? 3 groups of 5 each, right? So there's been some stuff floating around that I've seen where parents were like, oh my God, look at this crap, they said it was wrong. Well, officially it sort of is wrong, but that's where I disagree. You shouldn't like come down on a student just for doing it the other way. So how would I represent 3 times 5? Yeah, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that of course is still 15, which is where you're going to start to build up their understanding of commutativity. Okay, I like it.
Oh, I like it.
Sweet. How could I use a number line approach, a measurement approach to do 5 times 3? So this, let me before I get too far away, does anyone know what this is called? What does this really represent here? I can't remember, somebody said this.
Addition?
Yeah, isn't it 3 plus 3 plus 3 plus 3 plus 3? And what's this one represent? 5 plus 5 plus 5. So it is exactly the set method with addition. I love it.
Would that be a, that's multiplication. What, would it be an add-in or would it be a
Factor.
factor?
So that's coming up. Right now, we haven't done any missing whatever yet. So don't worry, that's coming up. And of course, that's going to be for division. Just like subtraction using a missing add-in, division is going to use a missing factor approach. Okay, I like it. So this is the repeated addition method, which is like, thank God math people sometimes can call things an appropriate name. We do have trouble sometimes naming things. So how do I use a measurement kind of approach? And of course, what does that kind of mean? That means using a number line. So if I want to do 5 times 3, how could I do that on a number line? Phew. Okay. Yikes. Okay. This is going to seem very like the same thing almost, possibly. Let's find out. So this would be 5 groups of 3. So that would be like if I take 1 step of 3. So this would be 5 steps of 3 each. So if every step I took was 3 feet, and I took 5 of those steps, how far would I go, right?
Oh.
Is that cool? I mean, that's exactly what I think of when I see this, kind of them stepping around. 1, 2, 3, 4, 5.
I'm writing down 11, 12, 13, 14, 15.
Yes, sir.
I've seen my daughter do that before.
Yes.
Is she wrong because she puts plus 3 on the top?
Plus 3? What do you mean?
Like,
Sir.
you know how they're keeping.
Oh, yeah. This is so that kind of reminds them that this is repeated addition. This kind of thing.
Yeah.
Yeah, that's good. That's sort of like what I did here, right?
Yeah.
Yeah. So it depends. That could be something you can add on at the end to reinforce that it's based on addition. So yeah, and again, every teacher's going to require different things on their little pictures. Yeah. Yes.
It's also going to help with like patterns when you count, like when you
What?
are learning to count up 2,
Why?
4, 6, 8, with 3, 6, 9.
Yes.
Oh wait.
Yeah, exactly.
You did it. You did 3. I was doing it by 5.
Okay, that's going to be what's here, right?
Because
3 steps of 5. So if I take a step of 5, and a step of 5, and I like what you just said about that reinforces the idea of multiples. And another step of 5, if I take 3 steps of 5, that still ends me up at 15. So both of those approaches reinforces commutativity. It reinforces repeated addition. I like it. Okay, cool. So let's get a little technical here for a second. By the way, real quick. Let me see, how do I say this? Is this coming in yet? Oh, that's coming in later, but. All right. Can somebody come up with a real quick, like 1-sentence word problem that would lead to this? I can remember somebody already did that. Like, how many people are there in this first thing? How many people are there?
15.
All right, well, let's see. There's 5 people. Let me say that. There's 5 people. And how much do each of them have in their pocket?
3
3.
coins.
3 coins in the pocket. So if they come all together, like let's go to the 7-Eleven or whatever, and let's see what we can buy, right? So they're going to pool their money. So how much money do they have? They have 15, some kind of, hopefully they're not pennies, right? Unless they can buy like half a stick of gum, right? So this is 5 people with 3 pennies, or whatever, 3 coins in their pocket. And this, of course, would be 3 people with 5 coins in their pocket, correct? Yes?
Yes.
Okay, I like it. Now, this is kind of neat. Remember this for division. Division is going to make a kind of a big deal about the difference between those 2 approaches. Yes?
Oh, when I was younger, I learned that division was close to subtraction and addition, multiplication is close to addition. Is that still true to this day?
All right.
Because we didn't have Common Core when I was in 3rd grade.
I understand.
But just
We definitely damn it when I was. All right, I'm going to blow some people's minds here. Subtraction does not exist. Did I say this already?
you did.
I did, right? Subtraction is adding the opposite, the inverse of something, right? And then division does not exist, right? And just to jump ahead a little bit, you guys all know this, I know. How do you do 8 divided by 2/3? Does anyone remember? How do you divide fractions? Multiply by the reciprocal. So isn't division really just multiplication? Yeah, and that works for everything. What's 8 divided by 4? It's 8 times 1/4. Okay, I'm sorry. That went beyond your question.
But yeah, no, I
Right.
understand.
Yeah, so there's obvious connections between them. And personally, I just accept that division and subtraction don't exist. They're just things we sort of created to mean something related to addition and multiplication. Okay. So let's get a little technical here for a second. So if I have A times B equals C, what are the names for Well, let's see. What's this result called?
Product.
Good. So it's the product. These are, of course, let's see. If C is A times B, what are A and B? They are what of C?
One's a factor?
Factors.
Are they both called
They're both
factors?
factors, yes. And that's why later, when we talk about division, we can use the missing factor approach. Okay, so we'll see that later.
The random thing about division, isn't there two things instead of like how they're factors? They would be a dividend and something else.
Yes.
There's two, right?
Just like with addition was addend and so forth, yeah. Okay. This one, it's like, are either one of these more important? No, they're equally important, right? In fact, A times B is B times A. It doesn't matter who's first, really, except, you know, like Common Core, they're sort of different. Okay. There's one little thing I didn't really talk a lot about back in chapter 2, and I think there was a homework problem about this, but let me see if you guys, it's called a Cartesian product. I can't remember if there's a homework problem that came up with that. Does that sound familiar to anybody? A little bit? And you had to go and read? No? Okay. Somebody's looking like they understand. So, Cartesian product between two sets. Let's see if this makes sense. It feels a lot like some property we're going to have to talk about here in a minute. But all a Cartesian product means is create every pairing that you can between these and those. Meaning, for example, AX is one answer, right? What else can you get?
AY.
AY. AZ, it's crazy.
BX.
BX.
BZ. BY. BZ.
Okay. How big is, let's call this A, let's call this B, and let's call this C. How big is A? What's N of A? What's the number in the set A? How many things are in set A? What's happening up there? There's two things, yes? How many things are in set B? 3. And how many things are in A? And here's the symbol. Now this is going to look very familiar. That's the Cartesian product. But I'm using sets. How big is the result? How many things in the result? 6 of them. So 2 times 3 is 6 is crazy. I like it. So that's another kind of set way, a way using sets to show multiplication. It's this idea of Cartesian product. It's really just counting elements in a set. Okay. Then we got our properties. By the way, just so you know, it's not going to mean you just talking all day. I do have something for you to work on here in a bit. Right? I don't know if that makes you feel good or bad or what. So obviously, what do you think about with whole numbers? These are all over whole numbers. Are the whole numbers closed under multiplication? So if I multiply two whole numbers, is the result always another whole number? Yes, right? If I multiply two whole numbers, can it come out negative?
No.
Hell no. Is it okay if I get 0 as an answer?
Yes.
Of course, because 0 is a whole number, right? So it's impossible to multiply two whole numbers and have the answer not be a whole number. Now obviously division screws that up, because then you get fractions which aren't whole numbers, and so it's not close. Okay. So whole numbers are closed under multiplication, just like they are with addition. What about commutativity? Commutativity. Holy shit, that sounds like a commutativity. Yes, okay. Is it commutative?
Yes.
Yes. And again, just to kind of highlight this, 7 times 2, get out of it. Now I got to make sure I'm being consistent with this. Well, we'll see. 7 times 2 is 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2. Is that 7? Whereas 2 times 7 is 7 plus 7. Yay! So this is read 7 2s, and this is read 2 7s.
Sorry.
It's alright. It's like you punctuate everything I say. Of course, what comes after commutativity? Do you guys remember from what we talked about before? You got commutativity where things can turn, can move.
Turn and you still get the same answer.
Do you?
You still, commutativity is so you can just flip the numbers, but you
Yes.
still get the same
So that's
answer.
commutativity. So of course the next thing would be associativity, where the parentheses can move, right?
Where the parentheses can be moved, but still can get the same answer.
And just to show you real quick. So this should be sort of obvious. If I did A times B times C, then that's the same as A times B times C, because if it's all multiplication, I could do it in whatever order I want to, right? Okay, I like it, I like it.
I'm gonna get water.
Okay. It was kind of like you were telling me to go to the next thing. What was this for additive stuff? What was this for addition? Identity. Identity? I love you, John. Identity. That's it. Okay. What was the identity for addition? What did it mean? What does identity mean?
It doesn't change.
Yeah. You maintain your identity after you do this. So what for addition?
1.
For addition,
Oh, 0.
0. Of course, for multiplication, it's 1. So the multiplicative identity is 1. And then we got distribution. I'm going to show you a picture here in a minute, but I want to show you something. Distribution, what does that mean? Like,
The foiling thing we learned? Yeah.
yeah, you can distribute the 2 and the 3 and the 2 to the 4. Yes? That's good old distribution. Now, of course, would you have to do that here? No, because I know what 3 plus 4 is. But distribution says if you did this, you would get the same result.
When I was in high school, we called it foiling. Do they still call that?
No. Foiling is when you have 2 and 2.
Oh.
Distribution is 1 and 2. So you distribute a single thing. Yeah. Okay, I like it. I like it. And everybody remember the FOIL stuff? If I had my way, we would never. Anyway, I'm not going to. I don't like FOIL. It's just repeated distribution. And of course, just to check this, 2 times 7 is definitely 6 plus 8. Yes? 2 times 7 is the same thing as 6 plus 8. Yes? Okay, all right. Now, why does distribution work? Why are you allowed to do that? All right, so let's investigate this. Would you agree with me that, why did you have to pick those? That's all right, Jeff, it'll be okay. Maybe I could, yeah, wait a minute, let me bring these guys back in. All right, I like it. Would you agree with me? I could be like the little dude right now. Let's see. Let me see, how do I want to set this up? Yeah. Let's see if Jeff can do this. I like it. There we go. Top. All right. So this is 2 times 3 plus 4, right? There's 3 plus 4, yes? That's 3 plus 4, yes, maybe? Is that freaking you guys out? Right, isn't that 3 plus 4? Yes. Well, yes. And then this would be 2 times 3 plus 4. So it's kind of like an area idea, right? 2 times 3 plus 4. Okay, so what is this? Still the same number of blocks. But this is, of course, what does this represent? 2 times 3?
Plus 2 times 4.
Plus 2 times 4. Cool, which is exactly what we did. Now, personally, I mean, that's kind of nifty. If you show it to a little kid, they're going to be like, oh, that's cool. We're not very impressed with that, maybe. So let me show you a different way for us to think about this. What does 2 times something mean without using multiplication? What does 2 times something mean? What's the most basic definition we had for multiplication at the beginning? Repeated addition. So what does 2x mean?
X plus X.
X plus x, 11. So what is 2m?
M plus M.
M plus m. So what is 3 plus 4s?
3 plus 4 plus 3 plus 4.
Yeah. Cool. So of course you get 3 plus 3 is 2 3s. 4 plus 4 is 2 4s, right? So then what you do is you just kind of notice the pattern and you say, why would I write this step? I would just go from here to here. I like it. And of course, distribution is kind of silly if I don't have a variable inside, because then of course I could just make it freaking 7 and double it. Okay. And then of course, anything times 0 is 0. That's fascinating. Now, real quick, let's see. Do I want to do this right? Yeah, maybe. No. We'll do that when we get to division. All right. So, tell you what. I've been talking for a while. You guys look like you're tired of me talking. So let me give you something to do. There's a front and a back to this course. But I've given you room between the questions. The 2 on the back are going to be really nifty, and I don't know what you feel when I say they're nifty.